Hello and welcome to Sovereign Moves. Don't forget to like, subscribe, and hit that notification bell for the latest insights.
There's a global conflict happening right now, but it's not being fought with armies or on traditional battlefields. It's happening at the atomic level. It's a high-stakes war for control over the single most critical technology in the world, angstrom-scale semiconductors. And the prize isn't land, it's technological sovereignty. And believe it or not, this entire global chess match really boils down to one single startling fact.
And this is it. This is the chart that explains everything. When you look at the most advanced chips on the planet, we're talking the brains inside every AI, every supercomputer, every next-gen defense system, a jaw-dropping 92% of them are made in one place, Taiwan. This incredible, almost unbelievable concentration of power in one single geopolitically tense spot, well, that's the fault line the entire global tech world is built on.
So here's how we're going to break this down. First, we'll explore the angstrom frontier to understand the tech. Then, we'll look at the geography of power, followed by the massive response called the American megafab, and finally, we'll game out the 2026 endgame. All right, Chapter 1. Let's start with the physics, because we are officially in what's called the angstrom era. And this isn't just some new marketing term. We're talking about a journey deep into the quantum realm of chip design, where the very laws of physics are being bent and reshaped to squeeze out more and more power. So what's really happening at this tiny scale? Well, for years, the industry standard was a transistor design called FinFET. But we basically hit a wall. We couldn't shrink it anymore. The solution is something called a gate-all-around, or GAA, transistor. The old design was like a gate controlling a flow of water on three sides. GAA, on the other hand, wraps the gate completely around the channel. The analogy here is just perfect. It's like going from a leaky ditch to a sealed bamboo tube wrapped entirely around a water pipe. The control is incredible, and the power leakage is almost zero. This is the absolute cornerstone of everything that comes next.
But of course, you solve one problem and a new one pops up. Even with these amazing new transistors, engineers ran into a microscopic traffic jam. See, on a chip, you have lines carrying data, the signals, and lines carrying energy, the power. And they were all fighting for real estate on the same surface, the front side of the chip. As we packed in more transistors, it created what they call the wiring wall. It's a complete bottleneck, a total mess of congestion that throttled performance.
The fix for this is, well, it's just brilliant. It's called backside power delivery. Companies like TSMC and Intel essentially flipped the script. They figured out how to move the entire power network to the back of the silicon wafer. This is a huge deal. It completely frees up the front side just for the signal routes, creating this pristine, wide-open superhighway for data. It's not just an improvement, it's a fundamental redesign of the chip in 3 dimensions. So what do you get when you put it all together? Let's look at the jump from TSMC's 2-nanometer chip to its next-gen 1.6-nanometer A16 process. The A16 combines that new GAA transistor and the backside power delivery. And the results? They're just incredible. You're looking at an 8 to 10% performance boost for the same amount of power. Or if you keep the speed the same, you cut power use by a massive 15 to 20%. Plus, you can cram 10% more stuff in the same space. This is not a baby step, folks. This is a giant leap. And this brings us to the price of power. Making these little miracles of physics is, as you can imagine, ridiculously expensive. A single finished silicon wafer using these new 2-nanometer technologies costs around $30,000. And that's not just a component cost anymore. That is the entry fee for any nation that wants to be a player on the world stage. Technological sovereignty now has a very, very specific price tag. Okay, Chapter 2. Let's pull back from the world of atoms and transistors to the world of maps and geopolitics. Because as amazing as this technology is, where it's located creates a massive, almost existential risk for the entire global economy. When you look at the foundry market, that's the business of making chips for other companies, there's really only one name that matters: TSMC. As you can see, they control a mind-boggling 72% of the entire global market. They are the invisible monopoly that makes the magic happen for everyone from Apple to NVIDIA. The entire planet depends on them. And almost all of that manufacturing might is concentrated right here, in Hsinchu, Taiwan. It's the undisputed epicenter of the semiconductor universe. But it also happens to sit right in the middle of the Taiwan Strait, one of the most critical and most contested shipping lanes in the world. This tiny island isn't just a factory, it's the absolute nexus of our global tech supply chain. Everything flows through here. This bizarre situation has given rise to a really powerful strategic idea: the silicon shield.
The theory goes that Taiwan's complete and utter indispensability to the world economy is its best defense. A conflict there wouldn't just be a regional problem. It would instantly vaporize the global technology supply chain, forcing pretty much every major nation on Earth to step in and keep the peace.
But, betting everything on a shield, no matter how strong, is a pretty risky way to live. And that brings us to Chapter 3, the absolutely monumental global response to this risk. An attempt to build a duplicate, bleeding-edge semiconductor ecosystem in the middle of the Arizona desert. The sheer scale of this is hard to wrap your head around. TSMC has committed $165 billion to build what they're calling a gigafab cluster in Phoenix. To put that in perspective, this is one of the largest foreign investments in U.S. history. It's a clear signal that the world is dead serious about redesigning this fragile supply chain. And this isn't a short-term project. This timeline shows a commitment that stretches out for decades. Fab 1, making 4-nanometer chips, should be up and running in 2025. Fab 2 brings 3-nanometer online in 2027. And here's the crucial part. Fab 3 is slated to produce the most advanced stuff, the 2-nanometer and A16 chips, by 2029. And the plans go even further, into the 2030s, with up to 6 factories capable of making whatever comes next, the sub-1-nanometer chips.
Now, an investment of this size doesn't just happen. It's all held together by a landmark agreement, what some are calling the Silicon Pact. You've got Taiwanese companies committing to massive investments. In return, the U.S. is offering big incentives like tariff relief. But the real game changer is that last point. The deal ensures the U.S. gets a full end-to-end manufacturing capability, including the super advanced CoWoS packaging. That's the key tech for stacking chips together, which, until now, you could only really get done in Asia.
And that leads us right into our final chapter, the 2026 endgame. With these huge new factories spinning up and the technology itself moving at lightning speed, what does the future of this competition actually look like? Well, it's a full-blown arms race, but the weapons are lithography machines and nanosheet transistors.
So here's the tale of the tape for the coming showdown. In one corner, you've got TSMC's A16 process. They're aiming for mass production in late 2026. Their huge advantage? They have a proven track record of getting incredible yields, and their ecosystem of customers is unmatched. In the other corner, you have Intel's 18A process. They're gunning for 2025, trying to get that first-to-market edge with their own backside power tech. Both are using the same fundamental new technologies, but their playbooks are totally different. This is the new front line.
So let's just quickly recap the whole story. It starts with this extreme, dangerous concentration. That concentration creates a level of risk that nobody can accept. The reaction is this massive global push to diversify, backed by hundreds of billions of dollars. And that leads to a totally new kind of deterrence, where the silicon shield isn't a single point of failure anymore, but a distributed network. And that, right there, fundamentally rewrites the global power map.
Which brings us to the final and most important question. After all this, hundreds of billions spent, an entire industry rewired across continents, what have we actually accomplished? Have we successfully copied the silicon shield, creating a more resilient, redundant world? Or have we just diversified the risk? Have we just created new, more complicated problems and dependencies that we haven't even thought of yet? The truth is, we don't know the answer.
This is the new reality. The defining global arms race of our time is being fought right here, at the scale of atoms. The winners won't be the nations that conquer the most land, but the ones that achieve technological sovereignty. The future of our economy, of artificial intelligence, of national security itself, it's all going to be written in silicon, forged in these incredible, glowing nodes of complexity, in both Taiwan and now in Arizona.
That brings us to the end of today's analysis. If you found this breakdown valuable, a simple way to support the channel is by hitting that like button. Make sure to subscribe and turn on notifications so you don't miss our next deep dive into the forces shaping our world. Thanks for watching Sovereign Moves, and I'll see you in the next one.